one that managed to remember that we are not on the regular time and regular place, which makes it more complicated for people. I know, and we sent it some time ago. But I'm very happy with our guest today, Juan Luis Gastaldi, or Hani, who came to us from Zurich, from our exchange program with ETH and the university, or from the ETH. Is a philosopher and historian of science. Specialized in the philosophy and history of formal knowledge, which means mathematics, logic, and computer science. And from the beginning of the 19th century to our days, his research focuses on formalization of meaning as a central problem of modern and contemporary philosophy, determined by a complex articulation between logic, mathematics, linguistics, and computer science. He has a very interesting, actually, CV of studying from his home country in Argentina to France, in Paris, in École Normale Supérieure. Among other, he studied philosophy and mathematics, and his PhD is in philosophy of mathematizations and logics of the 19th century. And from then he worked in Montpellier and in Paris again, and in Zurich, as I said. And I think that would be enough for the places. And his talk today, as you can see, is the language of mathematical epistemological consequences of applying AI methods to mathematics. So thank you very much.
Thank you. Thank you very much.
And he's here, what I forgot to say, is here for the coming month. So you are welcome to meet him and discuss things.
Yeah. Thank you very much, Shaul, for the very nice introduction, and thanks to all of you to be here, even though both the room has been changed and the hour has been changed, and it's a national holiday, if I understand correctly. So I really appreciate you being here, and more generally, thanks to the Cohen Institute for giving me the opportunity to come here for a research exchange for the next month. I will be around, so I will be very happy to meet anyone who would like to discuss things, or to know about your research, or to tell you about my research. So I'm really happy to be here for this exchange between the Cohen Institute and the ETH Zurich. So I'm also happy to be able to have this opportunity to present my my work at the very beginning. It's an honor and also a privilege to be able to do that. What I decided to do is to present some of the results of a research project which is coming to an end, which is one I was developing at ETH for the last years. Most of it is written in a paper which is under review, which means that all the feedback that I can get from you would be very useful to eventually revise that paper, because probably needs, if it gets accepted, will need to be revised. So I'm very happy to have this opportunity for that. And in particular, what I will be doing in this month is extend the survey of the beginning of this presentation. So I'm also glad to be able to present that here, since the next month I will be working on that. So it is almost trivial. This is the outline. Sorry. Yeah, so I was saying it is almost trivial to say today that with the massive development of artificial intelligence, of AI, or more precisely, deep neural network techniques in the last, say, 15 years, we are witnessing a real technological revolution. But it's less clear to see what is of philosophical significance in this revolution, if anything. And one of the reasons for that is that the conceptual perspectives frequently accompanying and even guiding those developments sometimes which sometimes are indistinguishable from ideology or advertising, involving vague claims about intelligence and optimization for the greater good of society, or involving dubious analogies between brain and machines and magical properties resulting from scientific procedures. All these things are usually very unsatisfactory to the eyes of philosophers and historians, in particular to the philosophers and historians of science, who are trained to suspect the ideological discourses that knowledge practices construct for themselves. However, my feeling is that there are many things of philosophical significance involved in this technical revolution, which might not be where the actors of the revolution would like everyone to find them. And in particular, I'd like to claim that there's something of epistemological significance in this process. Because as you certainly know, along the impressive evolution of practical applications of deep neural nets, the past years have also seen the application of these methods to different aspects of scientific research across the disciplinary spectrum, from natural sciences to social sciences. So the claim I would like to defend here is that the epistemological significance of these new AI techniques has to do with the nature and the role of language and science in or across the scientific practices. To such an extent that it might be difficult to obtain a better understanding of what is going on without a substantial renewal of our philosophical assumptions about language. However, a serious treatment of this question, or at least the one I would like to adopt here, which I call serious because I adopted, requires to avoid speaking about AI and knowledge in general, but rather to focus on specific cases. And in my case, I'd like to focus on the application of deep neural network models to mathematical knowledge. Indeed, somewhat surprisingly, mathematics has not been the exception to the general trend of scientific applications of AI. And as a rather picturesque piece of evidence, let me show you that recently two major figures in the field, Christian Szegedy and Gary Marcus, this is 2022. I'm sure if you're able to read something there, not that important either, it's just picturesque, as I said. They've made a bet on Twitter on whether by 2029, we will have a system with comparable or stronger capabilities than human mathematicians. Now, the case of mathematics is not just one among many other cases in sciences or in applications to scientific knowledge. The application of neural machine learning models to mathematics raises critical epistemological questions, mostly due to the formal, and by that I mean something like non-empirical nature, generally attributed to mathematics, which contrasts with the strong empirical position assumed by connectionist approaches guiding the application of neural nets or AI. So as such, mathematics defines that region of knowledge which is supposed to be the least sensitive to cultural changes as the one that might come from AI techniques. So while remaining very specific, the case of mathematics touches the heart of what is philosophically at stake in this question, at least to me. Now, unlike what people having listened to previous versions of this presentation tend to think, my aim here is not to defend machine learning methods in mathematics. Neither I want to criticize them. But my goal is to identify again, as I said, what might be of philosophical interest in them. More precisely, my claim is that these applications give us the opportunity to revise our conception of the relation mathematics maintains with its own textuality. And that this, in turn, suggests original orientations for a philosophical assessment of certain mathematical properties or mathematical objects or mathematical contents, however you want to call them, and with it maybe also some novel tools for the study of mathematical practices and more generally scientific practices. And I'd like to study how the problem of language, science, and textuality arises in this case, with the hope that one could eventually draw from it some clues for philosophically informed reconstructions of the formal devices associated to the production of knowledge in connection with the sign practices that define a culture. So I will first make a quick presentation of what neural nets are and how they are applied to mathematical knowledge. And they say a few words of what I think it's of philosophical significance here, before trying to understand what are the mechanisms upon which their success is based. And finally, if I have the time, probably I won't, I will assess some elementary arithmetical properties through the lens of those mechanisms to illustrate what mathematics might look like when seen under this new light. So I believe that by now, most of you have already had at least a Wikipedia approach to deep neural nets. And I don't have the time here to make a reasonable presentation, but let me give the bare basics to make sure we are on the same page. So artificial neural nets are basically devices for transforming vectors, let's say for transforming vectors. And if you don't know what a vector is, just think of a list of numbers. That's what a vector is, at least in this frame. So neural nets are just ways of transforming lists of numbers into lists of numbers. That's it. And their application to many fields rely, therefore, on the possibility of encoding some information as a vector, feed it into the device or the model, as it's called, and retrieving another vector, which can be decoded as some other kind of information. And the nature of the information does not matter much, as long as you can encode that information as a vector. And you have a fairly big set of examples of pairs of input and output vectors upon which you can train your model. As a matter of fact, the formal model of neural nets has been proved to be a universal function approximator, which means that given enough examples of input and output vectors, it will approach the function transforming one into the other if there is something like such a function. So in the most classical cases, the internal structure of the model is composed of a series of transformations, each of which has a similar composition. First, a linear transformation or a matrix, and you can see it here. You have a matrix, it's a linear transformation. Then you have a bias, which is a vector that you add to that transformation. And in the end, you have a what is called an activation function, which is a nonlinear function in the end, and you have it here. When you feed a vector into this is one layer. This is the structure of one of the layers. And sorry if you already know all this. So when you feed a vector into the model, the vector here would be this thing here, this list of numbers. Okay, it gets multiplied by the matrix. Then you add another vector, and then you apply the nonlinear function to each one of the elements of that list of numbers that you had. Okay, so that's more or less it. That's one layer of a neural net, and the deep nature of neural nets is given by the possibility of composing many of these layers. You have one layer like this one, and then you add another one, another one, and such that the output of one layer is the input of the next one until an output vector is produced. And finally, you train this model by iteratively updating the components of the matrices or the weights here, the things that are in color here. Each one of these is a number by which you multiply your original numbers, etc. And you update those by performing what is called a gradient descent on a loss function, which is another way of saying that you have a function which measures the error between the output that you get and the output that you would like to get. And you measure that error, and out of that, you adjust these values again, and you start again until you approach the right result through something that is called an algorithm that is called backpropagation. Now, this is, of course, an extremely simplified model, and current models have much more complicated structures, convolutional or recurrent neural nets or lately, or last years, everyone has heard about the transformers, and even the last year, I would say, or something, that diffusion models have become very, very popular. And also the training strategies might vary. You have supervised learning or training, unsupervised training, reinforcement learning. And in principle, we won't need any of these details in what follows. What is important is that all these variations remain particularly sophisticated cases of the basic model I mentioned before, which I hope to have given you a basic intuition of. So how do you go about applying these models to mathematics? Of course, there are multiple ways, and research moves fast. So I'm sure there are many applications I'm not aware of, but from what I've been able to see in the last years, I would say that the work in this sense falls into 4 wide categories. Depending on whether the focus is put on mathematical proofs, on mathematical objects, on mathematical skills, or on heuristics. Given the time frame, I will limit myself to say 1 or 2 words about them, but I will give a little more detail about one in particular, which could be useful to illustrate the whole. So in the proof-oriented approach, or what I call the proof-oriented approach, theorems are assumed to be the key to mathematics. And maybe for some of you this is obvious, but you're in front of 2 very good philosophers and historians of mathematics to know that mathematics might not be centered around proof. And this in the history is something that it's easy to show. So the fact that to center application of AI on proofs is a very specific choice, even if it's not sometimes presented as such. So the aim here is to train neural models to find proofs. And ideally, one would train the model on an extensive corpus of existing proofs, after which one could feed a yet unproved mathematical statement to the model, and the model would output a proof if there is a proof. Now, of course, in practice, things are much more difficult, and the research focuses on specific subtasks identified within the framework of already existing proof assistants or theorem provers, in particular things that represent bottlenecks for classical methods. And so you would train a neural net to try to circumvent that bottleneck. Sorry. So you have some references there. The slides are already available in my website, or I can make them available for you otherwise, if you're interested in this, in more details about these approaches. Now, the second approach would be the one that I call object-oriented, which is more or less the same strategy, but instead of feeding statements and predicting proofs, the idea is to feed the representation of some mathematical object, say a differential equation, and predict some property of that object, for instance, the solution to that differential equation. And here you can find other kinds of objects. Typically, there has been some work on series, mathematical series. So basically, you input the first terms of the series and you try to predict the next ones, or something that is particularly interesting, on at least from my perspective, is what they call symbolic regression. You enter something like a series and you try to find what is the rule of that series. So I know if you enter 1, 2, 3, 4, 5, 6, you try. The idea is that the model would predict that this is the symbolic representation of this is +1 or something like that. And this is done for, of course, a broad series or a large spectrum of series, but other possibilities of different kinds of objects can be found here there. The third approach is the one that I would call, for lack of a better word, something like knowledge or skill oriented. And the characteristics of this kind of work is a bit different from the 2 previous ones. The idea here is less to try to solve specific mathematical tasks than to endow the neural model with general mathematical skills capable of spontaneously solving mathematical related problems. And this, which would have been conceived as completely crazy maybe 10 years ago. I mean, why would something like that work, or based on which evidence? The hope now is motivated by this fairly recent revolution in the field of AI brought about by these new kind of neural nets that are called the transformers, which implemented a specific neural technique known as attention. And again, this is not the place to go into the details, but most of you, probably all of you, already heard about this through one of the most popular models that is around, which is GPT. GPT is an implementation of this transformer model, which puts at work this notion or this technique of attention. Now, one of the most surprising features of transformers shown by the authors of GPT-3, in the paper of GPT-3, you can find it, is the following. You can train this kind of neural nets on a huge amount of linguistic data, so natural language data, in a highly generic fashion, namely by trying to predict a random masked word in sentences. Just feed a sentence with some words being masked, and you ask the neural net to predict which words have been masked there. And once you have trained a neural net like this, as a language model, as you would call, you can present the model with a few examples of some specific task, and the model will be able to continue performing that task with surprising accuracy. This is called a few-shot learner or learning. For instance, once the model is trained, you feed a few examples of correct English grammar, and then the model is capable of fulfilling the task without further training. And this calls for very different kinds of tasks upon the same generically trained model. The same model is able to perform different tasks. This is what is behind the ChatGPT, if you want. Now, in the original GPT-3 paper, the authors already showed the arithmetical skills of such a model, in particular by trying to perform up to 5-digit arithmetic. And the results were pretty surprising, up to 3-digit arithmetic. This is 2018, 19, remember exactly, I think it's 18. So for 3-digit arithmetic, a model trained in this very generic way for natural language was able to achieve an accuracy of over, sorry, you have it here, of over 80%. I don't know if you're able to read there. This is 2- and 3-digit addition and subtraction, and the performance is over 80%. So for addition and subtraction, without any further training, without doing anything else than training in the way I mentioned. And these results have been improved by later models, and recent work showed that this capacity was very sensitive to the surface representation of the numbers. In particular, if you encode numbers as digits separated by powers of 10, as you have here, like written in this way. Sorry. So here, if you write it like that, then after fine-tuning on a pre-trained model, you can achieve almost perfect accuracy for up to 15-digit addition, which is like a lot. So following this new strategy, some work has been done, or like a lot of work has been developed in the past 2 or 3 years to test the mathematical skills of generic models, and then fine-tune them, like further train on a specific corpus for mathematical knowledge upon generic mathematical corpora. Now, the last of the trends I mentioned would be the one that I call heuristic oriented. And again, I won't say much about this one, but basically the idea is to guide the intuition of human mathematicians in searching for proofs for existing conjectures, or more precisely, machine learning methods here are mobilized to help understanding or verifying the existence of specific structures or patterns in mathematical objects. Okay. Now, in most of the cases, the results exhibited by these attempts concern only elementary mathematical properties, not high mathematics. Even though the last orientation actually showed a way to contribute to proving theorems in in the current state of mathematics. But of course, this part came mostly from the researchers themselves. But in the other cases, there are very elementary properties. However, the simple fact that these properties can be addressed, even with like only relative success, from the radically empirical perspective assumed by current machine learning approaches, this should already be enough to raise a whole series of philosophical questions within philosophy of mathematics. One could ask, for instance, what is it exactly that these models model or try to model? Is it the manipulation of abstract objects? Is it the manipulation of operations? Is it the acquisition of an existing piece of knowledge? Or the human capacity to produce new knowledge? Or instead the machine's capability of doing so? Or more profoundly, is the knowledge that one can attribute to these models a priori? And if it's a priori, why and how can an empirical learning procedure such as this one grasp that a priori knowledge? Or maybe mathematical knowledge, mathematical knowledge, or the knowledge that is grasped by the model is empirical, and then it's not mathematical. Or maybe mathematical knowledge is empirical after all. But then what distinguishes mathematical or mathematics, let's say, from other kinds of empirical knowledges? For instance, under which conditions does a data set constitute a mathematical corpus? If I take Wikipedia, I train it as I train a model on natural language, like a natural language model on that, and it actually is capable to perform arithmetic. Does that mean that Wikipedia is a mathematical text as such? And then would corpora from different cultures or different epochs induce different mathematical results? What counts as a mathematical result after all? And what kind of evidence can these models provide for the truth or the correctness or even the meaningfulness of these results? What is a proof? This list, of course, could be extended at will. However, it seems to me that the fruitful encounter between the philosophy of mathematics and current machine learning practices has not yet taken place. These questions are not being asked, neither by the people doing machine learning or AI, nor by the philosophers of mathematics. So to start remedying this situation, as I announced earlier, I would like to focus on what I believe is the most surprising aspect of this approach from an epistemological perspective, namely the relation between mathematics and natural language, or textuality, more precisely, writing in particular. And the reason for this is that texts, statements, expressions, symbols, characters, you name it, however you want to call them, let's call them texts. Texts are all these models can rely on to perform the mathematical tasks they are asked to perform. Whatever happens within the black box of neural nets happens on the basis of the processing of syntax and of syntax alone. Granted, the architecture of the neural net is itself not a purely syntactic object, but the implementation of a fairly well-specified semantic structure. But this structure is highly generic to the point that it can be successfully applied to very different kinds of data, images, language, sound, etc. You've seen this like in the press all the time, to perform significantly different kinds of tasks as well. So given the generic character, if neural models prove to be capable of dealing with mathematical content, such a content is nowhere else to be found than in the corpus of eventually supervised, textual expressions that are fed as inputs. Now, the idea that mathematics is a pure manipulation of syntax is not new, and it characterizes actually a formalist approach to mathematics, famously attributed to Hilbert. But with respect to those logical frameworks, machine learning approaches exhibit a significant originality, which is based at least on two aspects, I would say. First, without dedicated axiom systems, deductive rules, logical operations, symbolic reasoning, material manipulation, or access to any other kind of context than textual, most of the conceptual focus within this line of research is put on mathematical representations. But this problem does not look like anything that we have seen so far, because the objective is not to find the best representation for a given content, which one would call like a notation. It's not about finding a good notation, but the best representation for given texts, so that tasks assumed to rely on their unknown content can be correctly performed by a statistical learning model such as neural nets. Now, the second aspect is that while mathematical language conceived as an artificial language has been long time kept apart from natural language by different traditions in the philosophy of mathematics, neural machine learning models are led to operate novel articulations between natural language and artificial languages, which are far from philosophically trivial. In particular, the vast majority of the learning models used for processing mathematical expressions are those specifically developed for the processing of natural language during the past 15 years, or let's say 10 years. And this means that within this setting, mathematical expressions are treated as being themselves a sort of natural language. So in view of all these, I believe that the question that needs to be raised from a philosophical perspective is, what must mathematics be, given that models designed to analyze, reproduce, and manipulate natural language are able to grasp some significant aspects? And I think this is the philosophical significance of these methods, in particular in the case of mathematics. So the first step in that direction, the direction of trying to answer to this question of what mathematics must be for these models to work as they do, for models of natural language to work as they do, with respect to that, is to address the theoretical principles by which these models are supposed to be effective in the treatment of natural language, which again are not completely known. But these principles are not at all trivial, and at any rate, they are at odds with the ones invariably advanced by the tradition of the philosophy of language, which has been mainly interested in truth functionality and referentiality. In opposition to a referential approach to semantics, the principles of neural natural language processing are the ones associated with distributionalism. You might have heard of this. And in particular, what is called the distributional hypothesis, namely the idea that the content of a linguistic unit, let's say words, is determined by the distribution of that unit over a corpus. In other terms, the other units appearing in the context of that unit within a corpus. That's what determines the content of the meaning, if you want, of a unit. And this idea is not new. Particularly, it can be traced back to the structuralist tradition in linguistics in the first half of the 20th century, in particular, Saussure and Jemslev and Harris and Firth. But it turns out that machine learning models or deep learning models are not just retrieving this idea, but they are providing, maybe even unwittingly, a new computational interpretation of that idea. And this is what is called, or it's being called in the field, word embeddings. I don't know how many of you have already heard about word embeddings. I'm asking just to know if I can go faster. Two person. Okay, two people. So I cannot go three people. Okay, that's already something. I will try to present this. Let me see, what time is it? Okay, still have 15 minutes, should be more or less okay. Probably I won't be able to show the empirical results of mathematics, but never mind. Still, we have a month to discuss. So what are word embeddings? So the main idea of word embeddings is to represent linguistic textual units, let's say words, by a dense low-dimensional vector. Again, remember, a vector is just a list of numbers. So low-dimensional, that means that you have few numbers, not like millions of them, And dense means that these numbers are not zero. You have because that could be the case, just having one number and then a list of zeros. But that's what dense mean. I mean, you have different numbers in that list. So you would represent a linguistic unit as a low dimensional dense vector, which encodes the distributional properties of that unit. In other words, it encodes the information of the contexts in which that unit appears throughout a corpus. Now, the story of word embeddings is a beautiful story, like from the viewpoint of the history of sciences. And this is something that is happening for the last 10 years. So something very, like something beautiful is happening for the historian of science in these years. I don't have the time here to tell the whole story, but basically the point is that people were training these deep neural nets for linguistic tasks. For example, machine translation or sentiment analysis, anything that has to do with natural language. And these are different tasks. And at some point around the 2010, people realized that if you take the first layer of a neural net and you take it out and you plug it as being the first layer of a different neural net trained for a different natural language task, then the performance of the second neural net goes up. And this is surprising. I mean, they were not expecting this. They don't even know how to explain that. And one of the reasons it's surprising is because neural nets are supposed to be black boxes and not interpretable. They are not compositional. So why would you be able to take one part of it, plug it in a neural net that has nothing to do in principle, and get better results? So moving very fast here, moving very quickly, the idea then came of training that first layer independently of any task. And how would you do that? By training it to predict the next word or some word with respect to the context. And you just train that neural net, like that first layer, and then you use that layer as the first layer of all the other neural nets that deal with natural language. Well, when you do that, what you've just done is to have a vector for each word that you are inputting in the neural net that will function as a representation of that word with respect to any natural language model. And that's what a word embedding is. So how does this work? Well, basically you pick a very big corpus, like these are becoming increasingly big, and you input some sort of sentence or some fixed amount of words coming from that corpus. And for example, in this case, let me see. Yeah, you pick one word. In this case, it would be catches, and then you input the context of that word into the net. You input it as in this way. I'm not telling the details, but we can discuss about that during the discussion session. And you ask the neural net to predict the center word out of that context. And of course, at the beginning, the neural net will predict whatever, like randomly, but then you correct through backpropagation, and then you shift one word and you continue. Now you want to predict A out of 2 words to the left and 2 words to the right, or 5 to the left and 5 to the right. And then you do that across the whole corpus and probably with 5 or 6 passes on one corpus. And in the end, what you will have is that the layer here, the weights of the matrices that we have seen before, in this case, it's just one matrix because it's a shallow neural net, then will stabilize into some sort of list of vectors, each one of which corresponds to a word. And that would be your word embedding or your vector representation for that word. Now, once you do this, people realized that these vectors were not only good to improve the performance for some tasks in a neural net, but that they had some very strange properties in their own. In particular, there were 2 main properties that have to do with the semantics of the language. So let me show you here an example. This would be the first 25 dimensions of the word vector representation of the word house, and the last 25 dimensions, okay? Red being a positive value up to 1, and a blue being a positive value up to -1, okay, or down to -1. Now, let me reorder these dimensions so that I put for the word house, the ones that for which house has the highest values on the left, and the ones that have the lowest values on the right. Now, if I compare the word vector representation for house with all the other word vector representations of my vocabulary, I will find something pretty surprising, which is that words, I'm not sure you're able to read there. Can I zoom here? No, I can't. I can zoom in my iPad, but not there. But here you have the word bungalow. And it turns out that the word bungalow shares more or less a very similar vector than the one that represents the word house. And if I take a random word, let's say, what did I put there? Slowly, then it doesn't. So these word vector representations not only represent the words, but they encode some semantic content. And not only that, but now I have these vectors, I can add them and subtract them because they are vectors, and that's what you do with vectors. So if you happen to add the word, to pick the word house, and you subtract the vector corresponding to the word city, and then you add the vector corresponding to the word countryside, turns out that the result of that is a vector. This vector doesn't exist in your vocabulary, but the closest word or the closest vector representing words in your vocabulary would be that of farmhouse, which means that suddenly you are able to compute semantic relations, or as they call them, analogies, within the embedding space in which these vectors live. And again, this was also a surprise. People were not expecting this, and they still don't know very much how to explain it. Here you have other examples. This would be the embedding space. You have all the points that are words, and that means that all the words that have similar meaning are in the same space, clustered together somewhat. You have the value here with respect to house, and the closest points to the vector of house is houses, bungalow, apartment, bedroom, townhouse, residence, etc., etc. But also you have these relations such that if you take the vector for king and you subtract the vector for queen, the result will be approximately the same than taking the vector for hero and subtracting the vector for heroine. And this goes across a lot of other words, actress, actor, or landlord and landlady, and etc., etc. But also for syntactic properties like the comparative and superlative. And then, of course, all like a bunch of other wild properties of these things. Now, of course, all this looks like magic. I have 5 minutes to finish. Probably will take 5 minutes more if Shaul is okay. All this looks like magic because we know it's about using context distributions, but not so much how it is done. Now, interestingly, 2 researchers, in particular, one who's here at the Bar Ilan University, Yoav Goldberg, they showed, like in 2014, that these early models are implicitly factorizing a pointwise mutual information word context matrix. Doesn't matter what that means, but you need to get the idea that this is pretty basic linear algebra techniques, which are operating over a matrix which captures the association strength between a word and other words in the context. Okay. And on top of that, these authors show that equivalent results to the one that the neural models were getting can be obtained with explicit vector representations, in the sense of not being neural at all. So although current models are much more complex, these distributional representations are still the elementary building blocks of current models like GPT. Therefore, if we want to understand if and how mathematics can be addressed by current neural machine learning techniques, we need to understand how this particular perspective on language, the distributional one, can be able to deal with mathematical expressions and grasp at least part of their content, even before addressing the technicalities of neural models as such. Because in some sense, the properties that are responsible for the results of neural nets don't seem to depend or rely on neural network techniques. So how can I start approaching the end with all the things that I had imagined to present to you? So yeah, sorry, I haven't found those slides. So I think that to address this question, like independently of the technique itself of neural nets, and understanding what is the philosophy of language that is behind, it is useful to advance the notion of formal content, which is something I tried to do in this paper I mentioned before, by considering formal content as a way of characterizing that dimension of the content of words or of linguistic units, which finds its source in the internal relations holding between the expressions of a language. And this dimension is usually neglected from the referential or truth conditional, but also from the pragmatic or intentional standpoints which have dominated contemporary semantics or contemporary semantic theories. However, its role is well known across a myriad of sense regimes like poetry or music or art in general, or games and other rule-following practices, including law. And of course, formal sciences and mathematics in particular. If you think about mathematics, within the standard model of arithmetic, it is part of the mathematical content of the expression, say, 406, that when associated with the expression plus 326, it can be replaced with the expression 732. The set of all these relations, all the relations the expression 406 can maintain with all the arithmetical expressions, this set can then be said to characterize the arithmetical content of 406 to a large extent, whatever all those expressions might stand for, whatever the classical semantics or referential semantics you might imagine for numbers. So in an attempt to further specify the notion of formal content, bringing it closer to its operational conditions, I propose to identify three dimensions that seem to characterize that formal content. In other words, three different systems of relations between linguistic units contributing to their sense effects and derivable, at least in part, from the distributional properties of the corpus. And in this way, I propose to distinguish between the syntactic content, which is the content that a unit receives as a result of the multiple dependencies it can maintain with respect to other units in the context, the characteristic content resulting from the inclusion of a unit in a class of other units by which it accepts to be substituted in a given context, and the informational content related to the non-uniform distribution of units within those substitutability classes. So let me give you an example and then jump into the conclusion. Take, for instance, the unit gavagai, whose meaning is famously assumed to be completely or undetermined. However, as soon as that unit is put in relation to other units in an expression like the gavagai is on the mat, part of this indeterminacy, it's lifted, and the content, syntactic in this case, can be attributed to it as a result of the sense that expression makes. Likewise, much can be said about gavagai if we can establish that it can be substituted by cat, dog, bird, rabbit, spider, etc. And in this way, it receives something that I would call the characteristic content. And even more can be said about it if we know that the probability of this term of appearing is the lowest compared to all the other units in that class. So the work now would be to use this approach to try to characterize mathematical objects. And what I try to do in this paper, and that's part of the project I'm developing, is to characterize, in particular, elementary arithmetic arithmetical properties through these concepts, and give some empirical evidence for the possibility of defining mathematics in this particular way. Now, I see that time is almost up, so I will just, I had prepared ways of presenting you the empirical evidence of the way in which this could work. But again, we can leave this for discussion if someone is interested. But let me jump to some very few conclusions, and then we can open the discussion session. So the bottom line here is that, in particular, in the case of numbers, if you believe that properties like total order and recursive structure are essential features of the semantics of natural numbers, to the extent that it should be ensured, they should be ensured by an explicit definition, such as Peano axioms, in a way that any syntax expressing numbers should respect those semantic features. What I try to claim is that it might very well be that those semantic features can be derived from the distributional properties of the syntax, and of syntax alone, when that syntax is approached with the general tools by which we approach empirically the syntax of natural language. And one can imagine that what seems to be the case for semantic aspects of natural numbers would also be the case for other mathematical contents, such as series or differential equations or proofs or matrices or whatever you can imagine, provided some thought is put on it and empirical evidence is provided. Now, if this is true, the least that we can say is that this way of approaching and conceding mathematical content is a very strange one. And has been as such radically absent from the mainstream orientations in the philosophy of mathematics. However, as strange as it might be, I believe that this is what the suggestive results of neural applications in mathematics forces the philosophy of mathematics to think. And I think this is good news, because it's not that we are used to seeing new things happening all the time in the philosophy of mathematics. And in particular, I'd like to think that this novel conception of mathematics or mathematical content can be very useful for historically oriented philosophy of sciences, as well as for philosophy of scientific practices. Because in both of them, the study of scientific corpus or corpora, let's say writings or texts or representations, occupy a central role for the definition of these contents. And it's not clear that we have the right theory of scientific textuality to account for that. And this is particularly true in the case of mathematics and of the history of mathematics. On the other side, a philosophical account of these results can articulate the need, and maybe also the conceptual tools, for the explicit derivation of structural features underlying the syntactic data, and not be satisfied with black boxes and number crunchy approximations. The key here is this distributional conception of language against the referential or the truth functional one. And this has been the key so far. And I would like to claim that the key from now on might be drawing structural properties that might lie behind the distributional ones. So passing from a distributional hypothesis to something like a structuralist one. In any case, one thing seems clear. We're only at the beginning of machine learning applications to scientific knowledge, and we can expect their impact in the scientific practice to be significant for better or worse, and whether we like it or not. So the earlier we develop an epistemological understanding of what the problem is, the better prepared we'll be to critically address this challenge, but to approach the philosophical or the epistemological question of AI, one must focus on specific cases And it is possible that what is valid for one case, for example, mathematics, might not be valid for other cases, even like in social sciences or other fields, or that the reasons why it works in one case are completely different for another. So more general conclusions must be based on fine-grained articulations between these specific cases. And who knows, sorry, maybe we can get something useful out of all this. Thanks. Thank you very much. I'm sorry for exceeding so much of time.